Hello, everyone. So this time we're going to talk about the fundamental subspaces of A to kind of extend the ideas that you just learned about a subspace W and its orthogonal complement W perp. This has a number of really nice consequences. One is that it helps you better understand what the linear transformation that uses A as its standard matrix, what is it really doing? And then also a kind of a way to undo, not really quite, but like kind of undo the mapping in some way. And then also it has a nice consequence of showing you how to find a basis for the orthogonal complement. So I'll show you how to do so. First, what are the fundamental subspaces? So let A be any matrix. So it doesn't have to be square anymore, any matrix. The orthogonal complement of the row space of A is exactly the null space of A. And the orthogonal complement of the column space of A is actually the null space of A transpose. So then these are actually the four fundamental spaces: the row space of A, the null space of A, the column space of A, and the null space of A transpose. One of these statements we don't even have to really prove or explain because it comes directly from the other. For example, remember that if you were to take the row space of A transpose, that's the rows of A transpose. The rows of A transpose is just the columns of A. So then, of course, the span of these things is exactly the same. So the row space of A transpose is just the column space of A. So then if statement one is true, if this is true, then automatically this statement is also true. Just replace in the first statement, replace A with A transpose, and it comes automatically. So we're going to focus on the first one. This is, again, pretty important. It definitely just requires an explanation and a proof. So I'll give you like an outline proof. I'm not going to write completely out with words this time. Just quick symbols so you can understand what's going on. So suppose you have a vector that's in row A's perp. So then that means then that this vector X is orthogonal to every vector in the row space. But one of the theorems I gave you, though, that the only way that can be true is that it must be orthogonal to each of the rows, right? It has to be, because if it's in the row space, each of the rows is in the row space. So then it must be orthogonal to every row of A and vice versa. But if X is orthogonal to every vector in the row space, that means when you take the vector X and you take its dot product with any of the rows, you get 0. Well, that can also be written as a matrix multiplication. A times X then has to be 0. Because when you take A times X, you multiply the first row in a dot product with the vector X. So that entry will be 0. And again, that's vice versa. But if A times X is 0, that implies, and is implied by, that X is in the null space of A. So if X is in row A's perp, then it must be in the null space of A and vice versa. So these two things are the exact same set of vectors. So the four fundamental subspaces of a matrix are the row space of A, the null space of A, the column space of A, and the null space of A transpose. Now, if A is a M by N matrix, the row space of A and the null space of A are subspaces of Rn. The column space of A and the null space of A transpose are subspaces of Rm. They're not the same. Now, of course, they are the same if it's a square matrix. I'm going to draw you a picture to help you understand what the hell's going on. So think of it as a linear transformation defined by this matrix A. It takes a vector in Rn and sends it into Rm. But in Rn, you know the row space and the null space are orthogonal complements. So the row space, think of it like a plane. The null space is its orthogonal complement. So it's complement, it's orthogonal to that thing. And they only share the vector 0 between them. But in Rm, you have the column space, think of it as a plane, and the null space of A transpose, think of it as its orthogonal complement. And that's where the mapping goes. It goes from here to there. There's a few things about this picture, the reason I drew it, that is highly suggestive. It seems to imply that every vector in Rn can be written as a vector in the row space plus a vector in the null space. It's kind of implying that by the way I drew it. And also in Rm, every vector in Rm, I'm kind of implying that every vector in Rm can be written as a vector in the column space plus a vector in the null space of A transpose. And that's actually true. That's actually true. Something we're going to have to prove. It's really an important result. But then there's also something else that's going on. By the mapping, when you take Ta of x, you multiply A to x. That means that every vector here in the null space is getting sent to the 0 vector. But any vector, any other vector, any other portion of a vector is not. It's being sent into the column space. So the column space of A is the range of this particular transformation. There's something else that's kind of neat though too, because notice that on the right-hand side, I have the matrix A transpose. I'm going to think of it in terms of like A transpose. Well, if you take the transformation defined by the matrix A transpose, so A transpose is the standard matrix, it actually reverses this mapping. It takes every vector in the null space of A transpose, and it sends all of those to the 0 vector. And everything else gets sent to the row space of A. Neat, right? So T of A, its range is the column space of A. But T of A transpose, so it's this linear transformation defined by A transpose, takes every vector in Rm and sends it into the row space of A, which these are all things you actually knew already, just drawing in pictures to help you explain it. The really, really interesting thing here about the picture is that it's implying that every vector in Rn is a sum of a vector in the row space with a vector in the null space of A, and every vector in Rm should be a sum of two vectors, one in the null space of A transpose and one in the column space of A. You'll see how in applications, and about 2 more classes, where this is very important. So moving on though, you need to be able to find a basis for all these subspaces. And we already did a bunch of them. I mean, I've already done all of them. So I'm just reviewing this for you. Let's find a basis for the row space of A and the null space of A. Now, you already know how to do this from chapter 3. What you do is you take the matrix A and you find its reduced row echelon form. And then if you find all the rows that have leading entries in them, just take those rows and they are a basis for that row space. Also, because of this form, you can also find very quickly a basis for the null space by setting it equals 0, find leading coefficients, solving the leading variables in terms of the free variables, ripping things apart in order to get, in the end, a basis for the null space. There is a kind of a trick to it, so we don't have to do it quite so long. For every column here that does not, have a leading entry, there will be one vector in the basis. So then, for example, look here, this particular column does not have a leading 1. What I want you to do is put a 1 there in that column above it. And then for every column that does not, again, for every column that does not have a leading 1, put a 0. Now, for all the other columns, what you do is for this column here, find where the leading 1 is, and go to the column where I have my 1 in the column, and then take the opposite number. That would then be -2. Again, go down for the next column, go down to the place where you have a leading entry, and then go across until you get to the column where I have my 1, and take its opposite. That'd be then 0. That's one of the vectors, right? You can see it's right there. You can do it again if you like. This time I'll work from below. So then here are the 2 columns that have no leading entries. I'll put a 1 in one of them and a 0 in the other. And then I just go across. So then here's the leading entry. And I go across until I get to the column that has my 1. That's a 1. So I'll take the opposite of it and put it there in that column. In the second column, I have the leading entry of 1. I just go across until I get to the column where I put my 1. And the entry there is 1, put the opposite of it. And that's it. That's the script right here, right? That's a fast way if you want to read off these vectors. So you don't have to go through the process of solving it. I'm actually writing down the matrix equals 0, write down the linear system, solve the leading variables to the free variables, rip the solution apart. It's in the end the same thing. This is actually what people do. This is the preferred method. Okay. Notice though that if you take any of the vectors in the row space and take any of the vectors in the null space, the dot products is 0. Just because look at the basis vectors. Take any of the basis vectors in the row A and take any of the basis vectors you see in the null space of A, their dot products are 0. So of course, these are orthogonal complements to each other. Now, just to remind you how to do the column space, same thing. Take the matrix A, you row reduce it, then find the columns that have the leading entries, and then go back to the original matrix and use those columns. So that would be this. So this is the column space. And it's just the span of the first two vectors in the first two columns in A, because the first two columns have the leading entries when you go and row reduce it into its reduced row echelon form. Now, the last one, which we didn't do before, is how to find a basis for the null space of A transpose. You literally just take the matrix A, take its transpose, and then just solve that system. Take the A transpose, you put on 0, you row reduce that augmented matrix. When you do so, you can automatically read off the span by writing it as a system of equations and so on. But if you like, you can do what I did just moments ago. Notice this column doesn't really matter at all. It's actually the row reduced echelon form of A transpose that really matters. In that matrix, take the look at the columns that have no leading entries in them. There's only one, that's this guy right here. So put a 1 there. In all the others, let's say this column, find where the leading entry is and go across that column. And then whatever's there, just take the opposite of it. The next column, find the leading entry and go across until you get the column where I have my 1. Take the opposite of the number, that'd be 0. So the vector would be -1, 0, 1. Now I'm writing it as a column because I write it as a column because I want to make it easier for you to see it because the column space is written in terms of columns. So this way they're both written as columns. Remember, these are just vectors. Remember, these are just vectors. So then columns or row form, it doesn't matter. It doesn't matter. Notice that if you take any vector in the column space, specifically the basis vectors, and take its dot product with, well, the basis vector for the null space of A transpose, the dot product are 0. So of course, the null space of A transpose, its orthogonal complement is the column space of A. And that's it. It's nice, right? Really easy. Okay, so then that's the 4 fundamental spaces. That's why they are the way they are. And then that's just a reminder of how to find their bases. But we can use this idea to have a really cute way to find a basis for the orthogonal complement. It's really neat. The idea is that to find the basis for the orthogonal complement, the subspace W is spanned by a bunch of vectors. It has a basis. It's spanned by a bunch of vectors. Once you know it's spanned by a bunch of vectors, and these vectors don't even have to be linearly independent, by the way, they can be dependent too. As long as they span the space, it's fine. And as long as they don't span more, of course. Notice that the span of these two vectors is the same as the column space of this matrix. But from what I just told you, the orthogonal complement of the column space of A is actually the null space of A transpose, because those two things are orthogonal complements. And the orthogonal complement of orthogonal complement is the original space. So then when we can get the orthogonal complement of either one by starting with one of the subspaces and finding its orthogonal complement to get the other. So the orthogonal complement of W has to be the orthogonal complement of the column space of A, but the orthogonal complement of the column space of A is the null space of A transpose. So we just have to find a basis for the null space of A transpose. And we know how to do that. Now, this time I'll go back to the more traditional way. You write down the augmented matrix where it's equal to 0, you row reduce it, you write it as a system of equations, you then solve the leading variables in terms of the free variables, you replace the free variables with a parameter, you rip the vector apart, and lo and behold, there is the basis that we were after. Again, if you don't want to do all this work, You don't have to, because you don't really need this. You know, this is going to be the zero. You don't need this. You know, it's the zero vector. You actually don't need any of that. The only thing you need is the reduced row echelon form of A transpose. So then in that matrix, find the columns that do not have leading entries. That's this guy right here. It's only one. Put a 1 there. Now, for the other entries, go to the column that has its pivot. So for the first column, find the leading entry, and then go across until you get to the column with my 1. Take the opposite of that number. That would be -2. Then for the third column, go down, find the leading entry, and then go to the column where I put my 1, put the opposite of that number. And there you go. It's -2, 1, 0, like I just had before. Again, that's what I just did, is the preferred method to do this quickly. But it just, like, if you didn't actually do it the long way, you may not understand where things come from. So there you go. That's the how to find a basis for the orthogonal complement of a subspace. What's interesting is that notice that the basis for W is not actually needed. You don't even need a basis. As long as the vectors are at least spanning the space, you're fine. So that means that the vectors of W, they don't even need to be orthogonal. They just need to span the space. That's it. And you can find a basis for W perp. It's really neat. It's really neat. All right, I think that's enough for that video.